since it was brought up, this is probably a good time to talk about when you break a magnet, which I did on purpose, specifically for this discussion. If you take a magnet, North Pole, South Pole, and I break it.
Oh, Mr. Grant, you're so strong.
I know. Now, this was the North Pole. Now this is a South Pole. This was the South Pole. Now this is a North Pole. Well, they don't want to go together. So I've created two magnets. If I break this one, same thing. If I break this down ad infinitum, then now this is assuming that you can't break it down to the subatomic level. But yeah, you break it down, eventually you get to a single electron that will be a magnet that will have a north and south pole. Okay. So, you guys remember this, right?
Yeah.
This is our first Maxwell equation.
Gauss law.
Yeah. You want to see our second Maxwell equation?
It's like that.
It's also Gauss's law.
Right in what? Am I going to remember being seen this on the formula sheet? I remember that.
It looks like physics.
Equals 0. So remember, the first one tells you that a lone charge will create an electric field within its surroundings, right? And just as a heads up, this is the integral form of Gauss's law for electric fields. This is the differential form.
Oh my. Uh-oh.
Bro, why does that V have a line on it?
It's a triangle. It's an upside down triangle. It is the del operator. It's used for three-dimensional or higher dimensional derivatives. Okay, it's actually pretty complicated. You got to do vector calculus before you can understand this. This row here is charge density, so it's definitely closely related to the enclosed charge. What this says that when you dot del with a vector field, you call that the divergence of that field. The divergence of that field, say, through a Gaussian surface, says how many field lines, if it's positive divergence, it's how many field lines are exiting, a measure of the flux out emanating through, or starting from inside and going through to the outside of some arbitrary surface. The divergence would be negative if it was going in. And so this is closely related to that, but just like this equals 0, the divergence of the magnetic field also equals 0, which states that no matter what, if I have a magnet and I draw any arbitrary three-dimensional surface, it could be a sphere, it could be anything, it could be this right here, this shape right here. It doesn't matter. The magnetic fields, the amount going in has to equal the amount going out. And I see that by, noticing that this field line goes in, but then it goes out, right? This field line goes in, but then it goes out. Right? And so the divergence of the magnetic field is 0. It means you cannot enclose any part of a magnet where you have more magnetic flux coming out than going in, or more magnetic flux going in than coming out. And interpreting that in words means there's no such thing as a magnetic monopole, right? Like you were alluding to at the beginning of class. So you can't have a lone North Pole or a lone South Pole according to Maxwell's theory of electromagnetism. Right?
But if you think Maxwell's stupid, you can't.
Yeah, but if you think he's stupid, which I do, Maxwell, totally stupid. So that's the second Maxwell equation. It's not used very much. We'll actually get the third Ampere's law next week, and then Faraday's law not too long after that. So we don't use this that much. It is useful at a higher level, but in this class, it's like there's no magnetic monopoles. Full disclosure: have you ever heard of string theory, superstring theory? Ever heard of that? So it's a collection. There's a whole lot of different ones. But it's trying to improve on our understanding of the universe by kind of supplanting Einstein, kind of the same way Einstein supplanted Newton. And it's kind of trying to unite relativity and quantum mechanics, which is the holy grail of physics, getting relativity and quantum mechanics to work together without singularities and without infinities and denominators and stuff like that, which we can't do at this point. But what string theory The most popular version, first of all, predicts that there's 10 spatial dimensions, maybe more, other than our 3, this way, that way, this way. The most popular version of string theory says that there's 7 more, and plus the dimension of time, which is a physical dimension that exists in physical reality. That's what Einstein figured out when he developed relativity. So, and it works on paper. It works on paper. The math, I don't understand it. I've known a few string theorists in my day, or people that work on it, and I look at what they do and I'm like, yeah, whatever. Don't understand it. But apparently, from what they tell me, it works. It works on paper. Like the math works out. It checks out predominantly. The problem is it makes no testable predictions as of yet. There's no predictions that it makes that we can actually design experiments to test in reality. So, and that happens a lot in physics. There's ideas that work on paper, but then when we actually test them in reality, they don't pan out. So, but if it's true, if it is a more accurate description of reality, then string theory does predict, some versions of it do predict the existence of magnetic monopoles. So if we were to detect somehow magnetic monopoles in nature, then it would be pretty strong evidence for, or at least some evidence, because there's no evidence at all. It would be at least some evidence for string theory being correct. So thank you, Mr. Nelson, for making me waste the first 10 minutes of class.
No problem. Anytime. No problem.
Okay, but for this class, there's no such thing as magnetic monopoles. You break a magnet, it becomes a north and a south. Both pieces have north and south poles.
We
Okay.
haven't invented it yet in this class.
Yeah.
That's right.
Well, we did yesterday, didn't we?
Yeah, but we didn't invent the monopoles yet.
Yeah. Oh, maybe next week monopoles will exist then. Maybe they will. Okay. So yesterday we saw electric currents create magnetic fields, right? And I'm not going to hook it up because I'm sorry, it's a mess up here. I had to do something completely different in my AP Physics 1 classes, which are in here before you, and so I had to shuffle everything around up here, and now it's kind of a nightmare. So if you remember, when I ran electric current through this, the magnetic needle deflected, right? Let me get on camera. When I run electric current through this loop, the magnetic field moved, and if I put electric current through the other direction, then the magnetic field moved in the other direction. And we were kind of ending it there, but just to show the direction of the magnetic field. So let's say I have current in a wire that's coming out of the board. The magnetic field generated will go counterclockwise. And it's not like it just exists in that one loop. Like, it fills the whole space. It's wrapping around the wire, theoretically out to infinity, but the closer it is, the stronger it's going to be, right? So that's if it's coming out of the board. If you have electric current going into the board, then the magnetic field will be going clockwise. The B field, the magnetic field will be going clockwise. Okay. How we know what direction it is, so we don't have to memorize this and make it too difficult, we use the first of a few right-hand rules. I talked about this, did I get here? Yeah. At the end of class. So right-hand rule, I'm not going to say right-hand rule number 1 because you don't need to remember which is which, but there is a right-hand rule that will tell you the direction of the magnetic field. And what you do, you take the wire, you put your thumb in let's say the current's going up, put your thumb in the direction of the current that's flowing through the wire, conventional current, so the direction of positive charge flow, and your fingers curl around that wire in the direction of the magnetic field. So if the current goes up, magnetic field goes this way. If the current's going down, then it curls around in the opposite direction. Okay. And this is from the definition of magnetic fields. Magnetic fields, by definition, point away from north and towards south. Okay. So when we generate magnetic fields around coils of wire, then compass needles will deflect just like they would in the vicinity of a permanent magnet. Okay, according to the directions of those lines. Now understand that these directions are arbitrary, right? But we have to agree on these directions in order for the physics to make sense and to be consistent. So by definition, field lines go away from north towards south. By definition, field lines generated by currents are defined by the current, the conventional current that is generating it. Okay, so thumb in the direction of conventional current. If you want to be like one of those weirdos and be like, well, I want to use the actual direction of electron flow. Well, then just use the left-hand rule. Okay? What was that, Timothy?
So it'd be like you point towards the positive terminal of the battery? Or?
No, away from the positive terminal of the battery towards the negative terminal.
Okay.
That's the right-hand rule. Yeah. The opposite of what physically is actually going on. Yeah. Okay. So then we saw magnetic forces on currents carrying wires. These are pretty strong magnets. These are neodymium, the really brittle ones. That's why there's chunks of them that are broken out. If you're ever bored, look up the guy, I forgot his YouTube channel, but he gets those huge, several $100 neodymium magnets that have to be shipped in special crates that are much larger than the magnet, and they say danger on them because they can really, you get 2 of those and put it on either side of your hand, it'll literally crush the bones in your hand. They're so strong. He does crazy stuff with these neodymium magnets. They're really big ones. It's really interesting. But these are pretty strong even though they're pretty small. And so we saw yesterday that if I put an electric current through a wire that is within the vicinity of a magnetic field. If I put an electric current through here, yeah. So right now I'm going to put some electric current through the wire. On, off. On, off. Let me zoom in. On, off. On, off. What?
Don't forget to zoom out.
Yes, thank you.
Are you recording?
Yes. So on, off. Nothing's happening. Nothing's happening. That's because in order for a wire to feel a magnetic force on it, it must also have a magnetic field in the vicinity. Notice that the wire itself is not magnetic. Copper is not a magnetic material. If you take an actual, and I know this is a real magnet because it picks up a bunch of iron-rich paper clips.
Also stick to the side of the bar.
Yeah. Oh, yeah. That's a good indication, too. But it doesn't attract the wire. The wire is not magnetic. Okay. Wires, copper wires, if they were magnetic, they would be very difficult to deal with because in every piece of electronics, you got magnets. Almost every piece of electronics. Anything that spins. This is. Ever wonder what the inside of a ceiling fan looks like?
Not really.
Like that.
Ooh, cookie.
Bunch of wires. No, those are all coils of wire and a bunch of magnets and a little bit of grease. We'll talk about that when we get to electromagnetic induction. Okay, so in order for this wire to feel a magnetic force, it must have electric current flowing through it, and it must be within that electric current flowing through the wire must also feel the effects of a magnetic field. And if those 2 conditions are met, then you get a magnetic force. Right? Off, on. Off, on. Off, on. If I reverse the direction of the magnetic field by reversing that direction, then let's see which is which. So, I'm sorry, let's go back to the original one. This is the original one. That is a south pole because it's repelled by the north pole. So this is a south pole. So the field's coming in.
Wait a second. We're repelled by the North Pole? South Pole is? Repelled by the South, right?
Yes, you're right. Oops. Yeah. North pole of this magnet is repelling that one.
So it's a North Pole.
So this is a north pole, like I said.
Yeah.
So this is a north pole. So the field lines are pointing out this way, right? They're pointing. Let me try to make it. They're pointing towards you.
If you squint, you can see them.
So they're pointing towards you. The field line points towards you from this magnet. The current, the conventional current, is going down. So the current's going down. Magnetic field points towards you. The force is this way. Right? If I reverse the direction of the magnetic field, now obviously this is the south pole, so the field's coming in. So the field's pointing this way, current's going down, force is this way. Notice inevitably 3-dimensional, right? This is all 3-dimensional stuff. Electromagnetism, you got to be thinking 3 dimensions. If I just reverse the direction of the current, I just switched the wires from the leads, I just switched them, and now I get, it's back to going to your right. Okay? So it turns out that when electric current is flowing through a wire, and that wire sits within a magnetic field, that wire will experience a magnetic force. Okay. And how we indicate. Oh yeah, well, I did it yesterday, but this coil wire, I'll set it up again maybe later. I can magnify this effect because that's a pretty small force, as you guys saw. It's a pretty small force. Let me zoom out again. It's a pretty tiny force, but all we need to do, we need to get more current in the vicinity of the magnetic field, and we get more force. So if I just coil that wire up a bunch of times, then from the perspective of the magnet, oh, there's a lot more current in this, even though it's really the same current, but it just keeps looping back in the same vicinity of space, and so you get a much larger magnetic field. And so that's why when you see all the coils of wire in the ceiling fan, or all the coils of wire in my old pool pump, right? That's all wire in there. This pump is probably as old as you. That's why it just crapped out the other day. Well, it's designed to last like 10 years. And it probably went much longer because it's very rusty and gross inside. So yeah, it's all about more loops, more magnetic force, more effects. The more you can do, the more spinning motion you can get. That's all a pool pump does. It just spins. You know that, right? It's just like one of these little motors. It's like a drone propeller motor. Right? It does the same thing. You just attach an impeller to it that sucks water and just forces water out one end. Okay.
Pool pump propeller onto a drone.
I don't think the drone would fly.
Yeah, because it's pretty heavy. I think it's like 35 pounds.
Just get a really big propeller.
What if you put a jet engine in your pool?
It might damage the system. It might damage the filtration system. I would guess. Okay. So let's try to make sense of what we just talked about. Let's say I got a magnet.
Wait, that's a monopole.
Now they exist.
Yes, I just defined them into existence.
Oh man.
So we got the north pole of a magnet, and we got a wire, and we're going to run that wire up. So the current's going to be going up. I know that right here, I get a magnetic field that looks like this. Right? And I can tell you right now that the magnetic force on this wire will be into the board. So the magnetic force, which I'll call F subscript B, is into the board. Okay. The relationship, and someone alluded, I think, it's Gianni. Gianni alluded to this yesterday. He had some insight into what was going to be going on. Because it turns out that the magnetic force, I'm not going to give you the whole equation quite yet. The magnetic force is proportional, not exactly equal to. It's proportional to the current. The magnetic force is proportional to the magnetic field. And in fact, the magnetic force is proportional to the cross product of the current and the magnetic field. Now, in this context, we do have to consider the current direction to be indicated by a vector, because obviously you reverse the direction of the current and it gives you different results. So we do have to consider the current direction to be a vector. We'll piece that apart because the current itself is not a vector, but if we define the current in such a way, then part of that becomes a vector and it is pointing in the same direction as the current. So for right now, just consider the current to be a vector. Magnetic field is a vector. And so Gianni noticed yesterday it was a cross product. If you got things that are happening this way and that way, and then create something that goes that way or that way, three-dimensionally, the cross product is invariably involved. Okay. And by the way, this is the divergence of the electric field. This is the divergence of the magnetic field. The other two the other two Maxwell equations deal with the cross product of the del operator of Dorito. I like that. Of Dorito with the electric field. Cross product. And the cross product, again, you got to do vector calculus in college before you can deal with this. But it deals with the cross products of the electric field and the magnetic field. And it's really these two that govern. If you've ever seen electromagnetic radiation, like imaged on a graph or something, you see electric waves going this way, and simultaneously you have magnetic waves that oscillate perpendicularly to the electric field waves. It's because of the cross product nature of this stuff. Okay. So the del operator crossed with the electric field is called the curl of the electric field. This is the curl of the magnetic field, and it's kind of like what you think. It's kind of like curling around something, right? Causing some type of rotation. And so that's what we're dealing with here. And if you remember when we did rotation in mechanics, that rotation stuff, it's really truly cross products. Like the angular velocity of an object is the cross product of r and v, the radius and the velocity, and the tangential velocity. So yeah. Remember that the magnitude of the cross product is just I, B, sine theta.
I sine theta.
Get out.
IB sine theta.
No, I, B, sine theta.
Oh.
Get out. Get out. So this tells you the magnitude. Very, very often, theta is going to be 90 degrees or 0 degrees. So everyone together, what's the sine of 0 degrees?
0.
What's the sine of 90?
Wait, 1. Wait.
The sine of 90 is 1, and the
Sine of 90 is 1, sine of 0 is 0.
There you go.
Hey, you can do math.
Mr. the Great, I revoke the last name, your last name. Okay, so this is the magnitude. However, when we take the dot product of two vectors, we get a scalar. That's why when we determine the work done by a force acting over a certain distance, it's the dot product of the force and the displacement. The magnitude is force times displacement times the cosine of the angle, but the result is a scalar. Work is a scalar, right? Energy is a scalar. The cross product is a vector. The cross product, that's why when I have an object that's rotating this way, this is how in AP Physics 1 we talk about it's got an angular velocity that way, right? Vectors can't curve. Vectors are very specific mathematical constructs. They need to be straight lines. Okay? So I need to be able to talk about clockwise rotation here in terms of the straight line vector.
It can't be infinitesimally small straight lines that add up.
They can be, yes. And that's actually a very useful technique, yes. But kind of beyond the scope of this class. Okay, so I can define the angular velocity vector here in terms of, let's say, the radius that I draw when I'm talking about the tangential velocity of this guy. Or any point on the disk, it doesn't matter. You get the same result. The angular velocity, angular velocity, I don't want to go back to that. Let me just talk about with current and because I'm defining a new right-hand rule. That didn't just happen. Quiet, don't lie. Let's use the current and the magnetic field direction to define the right-hand rule, or at least demonstrate the right-hand rule. I know that the magnetic force in this situation points into the board. I also know that if this was a south pole, the magnetic force would come out of the board. I know that if this was a north pole and the current was going down, the force would be out of the board. And not just because I'm just flipping the direction, it's because I know the right-hand rule. The right-hand rule for cross products, there's a couple ways of doing it, so you got to pick one. The one that I like the best, pointer finger, finger number 1 in the direction of the first vector, which in this case is up. Next finger, second finger, in the direction of the second vector, the one that is crossed with the first. So it's going to be pointing this way. Right? Magnetic field's this way, current this way, magnetic field this way. And then your thumb points in the direction of the force, of the resultant vector.
I feel like Doctor Strange.
So check it out. I cross B, the direction is in the direction of your thumb, which in this case is into the board. If the current is flowing down, I cross B, thumb points out of the board, force is out of the board. Cross products happen all the time. Finger, the direction of the first vector, crossed with the second vector direction, thumb points in the direction of the resultant vector. Okay.
Yeah, you're definitely gonna have a lot of fun watching us do.
Yeah, I always do. It's good times. Good times. So that's how you know the direction of a force on a current carrying wire. Okay. Cool beans? Magnetized beans. All right. Also, do you think, now what happens if a current's flowing through the wire, through a wire, what's physically happening in the wire? Electrons are moving, right? Now again, conventional current says the current goes the opposite direction of the electrons moving, but you have moving electrons. So so do you think that the wire is actually necessary? For magnetic forces to act on charges? Do you think the wire itself is necessary? You just need moving electrons or moving protons or moving any charge. Any type of charge. An ion, it could be a beam of ions. That's what they use in the Large Hadron Collider, if you know about the Large Hadron Collider. Most of their experiments, they're accelerating hydrogen nuclei, i.e. they take the electron off of a hydrogen atom, so it's just a proton. So that's what they accelerate. Well, how do they can't just go in a straight line. They have linear accelerators, but those are very limited to how fast they can get the charges moving. So they actually use magnetic fields to curve the path of the protons as they're traveling around the collider until they actually crash together. They use magnetic fields, very strong magnetic fields. Yeah.
I think it's always funny, like whenever they say like H+1, like they do in biology for a lot of things, and it's like it's literally just a proton.
Yeah, just a proton. Yeah. And what's interesting, because the Large Hadron Collider, it's literally the largest, most expensive experiment or science experiment / construct that humans have ever created. And the tank of hydrogen that they need for an entire year's worth of experiments, it's like that big around, like that big. And that gives them the quadrillions of bazillions of hydrogen nuclei that they need. They're crashing millions of them together at every second, in this thing, and they're all contained in a single tank. I mean, I'm sure they have backup tanks, but
Doesn't 1 gram of antimatter they create at that facility cost like $1 trillion or more?
I don't even. They haven't made a gram. They haven't made a full gram, but
They estimate
it would be. Yeah. Oh yeah. Probably that wouldn't surprise me at all. Yeah.
Okay, I was gonna ask what the point of that is, just to watch things go boom, or.
What the point of creating antimatter is?
Oh no, of doing this spinny thing to
Oh, it's to study the physics of the very small. This is quantum physics. What's real interesting, because a lot of people are like, how do we know so much about the early universe? Because obviously no one was here. Obviously the Earth wasn't even here. The sun wasn't even here. So how do we know so much about it? How do we know what conditions? Because we know what the conditions were like. A billionth of a billionth of a billionth of a second after the universe started. We know what the conditions were like in the universe. Because we can recreate them here on the Earth in particle accelerators. Just within volumes so small that it's not dangerous, right? But when you accelerate protons to within 99.99999% of the speed of light in one direction, and then protons in the other direction at the same speed, and then you crash them together, the energy density that's associated with those collisions is just like the energy density associated with the early universe. And by early, I mean within a billionth of a second after the Big Bang. So it's for pure science largely, right? But then it's also to probe You know, quantum mechanics, the quantum realm, the physics of the very small. Yeah.
Is it more expensive than the hologram of the moon?
Wait, what?
Is it more expensive than the hologram of the moon?
It's comparable. Comparable, yes. Shh. They might not know.
There's a microphone in that speaker.
Gotta edit that part out.
I wasn't gonna wait in line for like 12 people to use the bathroom.
Huh?
I wasn't gonna wait in line for like 12 people.
Is there that many people?
Yeah, because everyone's having to go to that one because I don't know how many other ones are open.
I just push somebody out of the way or share.
Share? Okay. Anyway, we got a little sidetracked there. All right, we good. So, going back to what we were talking about before Aliun derailed our conversation. You don't need a wire in order to have the magnetic force act on charges. All that has to happen is that the charge needs to be moving. So yes, it's easy to see in wires. Yes, having charge move through wires is what allows us to design things like electric motors and generators to handle electricity, at least at a useful level. But we don't need to. You don't need wires. You can just have moving electrical charges. And where's my magnet? Wait, where'd it go? Moving electrical charges within magnetic fields, and you'll get magnetic forces, like you do at the Large Hadron Collider. So this thing it's kind of a cheap one, but it's still kind of cool. This is an electron gun. So that blue light is actually, I think it's a radiation. You guys know that if you need to stand up, go ahead and stand up. You guys know that when electrons change energy levels in orbitals, they emit photons of light, right? Yeah. We'll actually learn about I'll show a video that will describe it, because you might have wondered how that process actually works. Why does an electron changing energy levels emit photons of light? Well, it turns out anytime an electron accelerates, it will emit photons of light. And so what you're seeing here, that blue light is literally accelerated electrons giving off that electromagnetic radiation. You're seeing electrons moving right now. There's this little plate here. Electrons are jumping off that little plate in all directions because of the voltages applied. But then there's a little slit here, and then on this thing that's glowing green, it's glowing green because the electrons are striking that surface, and it's a phosphorescent, there's some kind of name for it. Photoluminescent, something like that. But whenever electrons strike that surface, it emits a green photon. And so we see the green color of light. If you look closely, it looks like, and if this was designed well and constructed well, there would be a vertical line of green light on that little face right there. Can you see it, Gianni, kind of? Yeah. There's a little bit of a green line, but it's sloping up to the right here. But what that's showing you is that because there's a little disc. Let me actually turn the light on real quick. This is what's happening here. Oh, and I should probably zoom in on it. I hate teaching like this. I hate it. In this tube, there's a post with a little plate on it, and that's connected to the electricity. So this is where the electrons are all jumping off of. And then there's a plate under here that's parallel to this guy, so it's perpendicular to you guys. But then there's a slit cut through it, and then you have that fan that comes up there like this. And so what this is supposed to do, the electrons are jumping off in all directions, but when they go up through that slit there, then they're supposed to make a line, a vertical line. Okay. That's what we're supposed to be seeing.
That's sort of like a CRT.
Yeah, exactly. Yeah. A CRT is a cathode ray tube, and we're going to talk about those for sure. That's how they discovered the electron, right? In the cathode ray tube. That's what old TVs were made out of. So if I those are moving electrons, and the ones, they're kind of moving straight up, right, at the top of that little plate there. And so if I bring in a magnetic field, I should see a deflection of that little line. And sure enough, I see, there we go, that's better. See now I've got it almost vertical, but now I can change that. If I get close enough, do you see the little flashes? Yeah. That's when the electrons are, bam, hitting that thing hard. Right? So if I play with it down here, it looks like I'm moving light around, but really I'm just causing a change in acceleration of the electrons. Oop. These strong magnets. So, and what's cool is that in college, you'll most likely do an experiment where you use a setup similar to this, but is more complex and more sophisticated, because you'll be able to take a straight visible beam of electrons, apply an external magnetic field, and have it curve in on itself. And by measuring that curvature, you can work out, this is what J.J. Thomson did, you can work out the charge to mass ratio of the electron. He couldn't figure out in that first experiment what the charge was and what the mass was, but he could determine that ratio. And then another guy named Millikan came along later and did this oil drop experiment that was ingenious, that he was actually able to piece it together and determine the actual charge on the electron and the actual mass of the electron. It's pretty important. Okay. So
that's why you're not supposed to put magnets near old TVs.
Yeah. I mean, that's what old TVs, that's what they would do. They would shoot beams of electrons out at different energies, and then you'd have the thing that would apply external electric and magnetic fields that would guide the beam to where it needed to hit on the screen. If you ever looked at, I think the slow-mo guys did it with like a Super Mario Brothers, where they showed someone playing but they slowed it down enough to show what actually happens on the TV screen. And what you see all at once is really just like line by line, electrons hitting the screen real fast, from top to bottom. It looks seamless to you because it happens so fast, but it's literally little tiny line by line. The image appears on the screen. It's very strange. And it's using electrical signals that allow, because it's not like you can plan that and do that in real time. You can't design so. You just have to have it based on the existence of the electrical signal. It's really interesting stuff. Really interesting, complex stuff.
Do they still make them?
Probably not. They make cathode ray tubes because they're used in physics classes all the time. And they might have some practical applications, but
I
I'm
think
not.
it's like for medical devices, like X-ray scanning and stuff. Like nothing
I
much.
think cathode ray tubes do have something in medical.
Yeah.
Do you have what?
I think they have some purpose in the medical field.
Okay. Yeah, I don't know. Definitely beyond the scope of this class.
I'll let you know.
Okay. Too bad we don't have any future doctors in here.
Yeah.
What?
Or at least people smart enough to be future doctors.
Yeah. Okay. So, what I was showing you there is that all you need for a magnetic force is a moving electric charge and a magnetic field, an external magnetic field. So if I have something like, and this is probably let's say I have an external, and let's consider it to be uniform magnetic field. And then I take an electron from an electron gun and I shoot it. Actually a proton, let's say a proton. Notice, if I had electrons actually going through a wire, right? They move in the opposite direction of conventional current. So if you wanted to be like, I already said this, but if you want to be like, all right, well, I want to use the direction of motion of the electron, you got to use the left-hand rule. Same thing with the left hand. If you have an electron that's just flying through space within a magnetic field and you want to determine the direction, you can either use the left-hand rule or you can just use the right-hand rule and reverse the result. Okay. Positive charge is moving this way in a magnetic field pointing up. I cross B forces out towards you. If that was an electron, I cross B, flip it for the electron. Negative charges do the same thing but opposite. Okay. So let's consider a positive charge though. Positive charge Q is moving within this external field, kind of like I just showed you with that setup here that's blocking rid of this field. So let's say this guy's moving this way with some speed v. Well, now we don't have an actual current. Now we just have an electron moving. Okay. And it turns out that the magnetic force on a moving charge, and this is very similar to current, only the current is not constrained to a wire now. the magnetic force is proportional to the speed at which the object is moving, the charge is moving. So the faster it is moving, the larger the magnetic force. The magnetic force is directly proportional to the magnitude of the charge. So larger charges get more magnetic force. And it turns out that the magnetic force, when I take these proportions and tie them together into an actual equation, is equal to the charge times the cross product of the charge's velocity and the magnetic field. This is not technically on your formula sheet, but it is in a way that's almost identical. I'll show you that in a second. So, there is an angle here. There is an angle. Theta. There's an angle between B and V. So if I wanted to calculate the magnetic force, the magnitude would be Q times VB sine theta. But the direction is still going to be mutually perpendicular to both. So if B and V are in the same plane, doesn't matter what the angle is, the cross product is going to give you a direction that is mutually perpendicular to both. Okay. And I can use again the right hand rule. V cross B. Right now it's not a 90-degree angle. V cross B. My thumb still points into the board. So this positive charge here would feel a force, magnetic force, into the board. If it was negative, I use the right. This is how I do it. If you want to use a left-handed rule, that's fine. But I'm not left-handed. I don't like left-handed people. I'm just kidding. I do it right. If this is a negative charge, V cross B. For a positive charge, it's that way. So for a negative one, it's flipped. That's it. Okay. On the formula sheet, it says this. It drops the parentheses. I feel like the parentheses, until you know vector calculus pretty well, kind of help conceptually, but this is what's on the formula sheet. But remember, if I'm calculating, and these are vectors, I don't know why I'm not putting those there. If I'm calculating the magnetic force, the magnitude of it, then it's going to be the magnitude of this, which is just going to be Q, V, B, sine theta. Again, very often theta is 90 degrees, in which case the magnetic force is QVB. Okay? QVB is not on the formula sheet. This is on the formula sheet, right here. This is on the formula sheet. So you got to get QVB from this, or QVB sine theta. Sometimes the angle is 0, right? What if the angle is 0? That means the positive charge is moving with the magnetic field. What's the magnetic force?
0.
0.
Yeah.
Isn't that weird?
Sure.
So weird.
You find that weird?
Yeah.
Just because it's moving in the same direction as the magnetic field, it feels no force. But as soon as it starts moving in a direction that's not parallel, then it starts feeling, it's weird. The reason I point that out, that it's weird, is because it took Einstein to figure out why. It took, and again, the follow-up from that video that I showed you the other day, the collaboration between minute physics and Veritasium, the follow-up to that video shows why. Shows why you have these weird, strange properties of magnetic forces on both charges. And same thing with a wire. If I ran a wire down this way within this magnetic field and ran current through, it feels no magnetic force. Okay. So if you're trying to get electromagnetic stuff to happen, you want stuff to be perpendicular. You want a magnet pointing the magnetic field this way, and you want wire going perpendicular to it. Because then those cross products are maximized and you get maximum magnetic forces. Okay. Cool beans?
Forcefully magnetized beams.
Can you make a bean a magnet? Would it be possible?
With a nudge.
I don't know.
Because I know it's like Cheerios have like a very slight bit of magnetism to them.
Well, it's because they have iron in it, right?
Exactly. Yeah, they put a bunch of iron in it. So if you have like Cheerios floating in water, you can actually like slightly attract them with a magnet.
Since water is polar, do magnets affect it at all?
It's overall neutral.
Right, but like an electromagnetic field does, so why is that?
What do you mean
Like
affected?
a microwave oven will make the water molecules oscillate.
Well, that's because they absorb the electromagnetic radiation.
Right.
But that's just because they're comparable in wavelength size.
So can a changing magnetic field affect the water at all?
Well, I guess so, because that's how the magnetrons literally power microwaves. And that's why your food gets hot and your plates don't.
Yeah.
Because the water molecules, they're on the order, they're comparable in size to the wavelength of microwave radiation. That's what microwaves are not powerful. Microwaves are not super high energy waves. It just so happens they're really, really good at being absorbed by water molecules because they're essentially the same size.
Which is also why stuff dries out in the microwave.
What happened, Graham? Are we gonna have time to watch that joke tomorrow?
Um, Maybe I do need to finish this up. We probably could have finished today, but you guys kept bringing up stuff that was beyond the scope of this class and
Being smart.
being super annoying. I mean, being smart. Bye, everyone at home.